My name's Ryan McNulty, and my project's name is Do Turtles Have Favorite Colors? So I've had turtles for a long time, and I've always been interested if they had favorite colors, and even if they could see it. So I did research, and I saw polls that said turtles. They took a poll, and they said turtles most likely can see color, and they also are more sensitive to like bright colors like red and yellow, but more like they're more attracted to like soothing colors like blue and green. So I conducted an experiment by setting up a boundary with like pillows and stuff so he didn't crawl out. And I also set up like a line of colored sheets of paper with food on them so they can so my turtle could choose his favorite color. And I have a video if you want to see it. Okay. So as you can see, my turtle is turning away from red and going right to blue. So after I conducted this experiment, I put my data into an Excel spreadsheet, and red never got chosen, and blue came in first. So that blue was the favorite color for my turtle, and most of other people's turtles too. So I can guess that that's the general favorite color for turtles. And green and black came in second. They both got 5. I conducted the experiment about 22 times. And so I put my data into a graph, and then I brought it onto like an ideal road intersection for turtles. So basically, my purpose of the experiment was to help turtles cross the road without getting hit by a car. So I bordered everything, all the dangerous parts by red because it won't go on red. And I put a safer part with blue across the road to make drivers more aware of like where the turtles will most likely cross. And I put it in the corner so he wouldn't go right into the middle of the road. And basically that's it.
So what's a thermocouple? A thermocouple is basically like a thermometer. As you can see here, we snaked one thermocouple down into the house, and inside the house it will take the temperature of the house. And then we also taped one outside the house to take the outside temperature of the room. And then when you minus the inside temperature of the house from the outside temperature of the house, you get the difference, and that's what we were measuring for. And also our heat source was a 60-watt incandescent light bulb that you can see right in here.
Okay, so our conclusion was correct that the styrofoam would work the best, and it did, because most of the households have styrofoam as their installation.
And as you can see in our graph, so we measured it in 10-minute intervals, and then this is the temperature rise or difference, and this is the time. And you can see significantly that the styrofoam worked best. It had a 34.3 degree temperature difference.
This is the eco-friendly paint. It's water-based, so it doesn't contain as much harsh chemicals as the other two do. And so for our procedures, we had tanks filled with water, and we submerged in them boards that were coated with the paint, and then introduced brine shrimp eggs to the system. And then after a while, and once the conditions were optimal for hatching, we counted how many had hatched over a period of time, and then we graphed our data to determine the hatching rates for each paint. And the results concluded that the eco-friendly paint resulted in the highest hatching rate, while the zinc and copper paints resulted in the lowest hatching rates. So that means that the zinc and copper paints were the most toxic, and the E-paint was the least toxic.
Hi, my name is Ben Brown. My project is biology. It's testing effects of water temperature on how much shrimp eat. I used a mono shrimp, and that is a kind of freshwater shrimp which can be found in Japan, Taiwan, and other parts of Southeast Asia. So I thought that as the water temperature went up, they would eat more, which ended up being true. So every night I fed them a pellet, which is this big before it goes in the water, and in there you can see after like about 2 hours now how much it has gotten bigger, and how much softer it is also, so the shrimp can eat it. And also when the shrimp eat it, I looked at how much they ate, whether it's half of it, or 3/4 of it, a quarter of it, or all of it. I looked after 1 hour and then 8 hours, which would be about morning. So this is important because global warming, if it sort of really happens, then they'll be eating more. They will also be moving around more to get that food, and then that'll make it so they live for less time. And then if they live for less time, they'll have less time to reproduce, so that their population will start to decline. And then if this happens with other populations, they'll also start to decline. And then all those populations will decline. And then they'll be eating more, so that there's less food available. So all animals in the ecosystem are affected, and are then going to eat less, or have to eat less, even though their bodies want them to eat more. So that's going to create a mass extinction because of global warming.
Hi, I'm Joey Calabrese.
I'm Stuart Irwin.
That's Stuart Irwin. Our project, we decided that we would build a robotic hand, or a prosthetic hand. The main field that this falls under is a field of biomedical engineering. But in performing and taking part in this project, we discovered that not only does it involve biomedical engineering, but it also involves electrical engineering, software engineering, mechanical engineering, as well as 3D printing. There was a lot to go over, but essentially the big overview, we took a software code on the computer, tweaked it so we altered the degrees in which the motors here will function. And when we changed the degrees, we would download the code and upload it to this computer chip right here. And when we uploaded it and downloaded the code, the computer chip would be ready. And after that, we needed to wire the computer chip to the motors with the use of this breadboard. The motors need 3 electrical impulses to be able to run. One is the grounding wire. Another is the 5 volts of power that we've used. And another is a pulse width modulation signal, which the motors need to know when to switch their motion. So there's a lot of intricate wiring, all funneled into one connector piece, in which we connected these wires are the wires of the motors. And as soon as those motors were connected, transitioning to the mechanical engineering aspect, we attached these plastics to the motors, which in turn are with this, I don't know if you can see this fishing line here, and the fishing line is actually wired through into the ends of the fingertips on the hand here. And as they're wired through, the motor will rotate, and the left string on each motor will contract the hand, and a right rotation will expand the hand. Unfortunately for the software aspect of this project, we were only able to code the hand to go like this, and even then we downloaded a sample code and just tweaked the degrees in which the motors would rotate. But after all the wiring and all the assembly of the hand, which we will talk about after the demo, you turn this switch on here, which turns on the capability for the servos, and then the computer will give a 5-volt power supply to the computer chip here. And when plugged into a USB, the hand will move.
I'm Lucy Pritchard.
And I'm Erin Flynn.
And we were really interested in whether or not there was a more eco-friendly alternative to the Dawn cleaning solution when you're cleaning waterfowl after an oil spill. So we thought at first that the Dawn soap would be better than the other ones.
Because it's more advertised.
Yeah, it's more advertised, and no one else really says anything about that. And so we used some olive oil, and a certain amount of olive oil, and we put it on a feather. And then we let the feather sit for 3 minutes in a basin with that amount of oil on it. And then after the 3 minutes were over, we'd scrub the feather for 15 seconds with the type of soap that we were using. And we had 4 different soaps that we would use, and they were
7th generation, Greenworks, Dawn, and Myers.
and we were mostly comparing the Myers 7th generation Greenworks to Dawn. And after we'd scrub them over a basin, we'd move them into a measuring cup that had water in it, and the oil and the water would separate. So the oil would be right here, and the water would be right here. And then we'd just measure how much that was. So say that was 10 to 8. We know that's 2 ounces. So that was really important. And over here you can see that Dawn and the Myers soap, which are pictured down here, removed all of the oil, while the Greenworks and the 7th generation didn't quite get all of it. So we thought Myers was the best because it's the more organic and it's a solution that's better for the environment. And this was like really important to us because when we're older, we don't want our children to be like swimming in beaches and there's oil and all these animals are covered, and we just really think it's important for the future.
Hello, my name is Ziad Ali,
Hi, my name is Kisak Lee.
and we did the effects of a rise of temperature on green bean growth.
So in our experiment, we were simulating a global warming situation. So we used night lights as our global warming heat source, and they were on for 24/7, and we put them inside these huts, which were wrapped in saran wrap, and that was like the atmosphere effect. And we wanted to see how our plants would react to the extra heat being generated.
As you can see, after 24 days, the control plants were pretty much, the experimental plants with 1 bulb in it, which represented our expected
global warming
global warming, grew really fast in the beginning as if it was on steroids, and then eventually slowed down and then died due to lack of water. The experimental with 2 lights.
That was extreme test, not the actual global warming, but extreme like heat test to see how it would react. And then the control was like our utopia, where there's no such thing as greenhouse gases, and everything is perfect.
The experimental with 2 lights went up really high, but then eventually crashed down due to lack of water.
Hi, I'm Alex Hill. And I'm Ian Rowett. Yep. And today we have an IZOD impact test machine. That's what this is. And what we were looking at is the chemical properties of different materials that would be useful in automobile crumple zones, which is a safety feature which is absorbing energy during a collision. So Ian, if you'll be so kind, what we did is we notched various samples of material, and we will load it into a vise located at the bottom of the machine. We'll clip it in there, and then we'll raise the hammer up to a certain angle right here, 90 degrees. We allow it to swing. It breaks cleanly, and what we'll do is later we'll take a look at footage we collect during that test, we'll take a look at the angle that occurs after the collision, and we'll use that to find the amount of energy that was absorbed by the sample during the collision.
I'm Nicholas Russo. And I'm Madison Sott. And we are doing the effect of visual appearance on pasta. Our question is, does visual appearance have an effect on what type of pasta you pick? According to modernfarmer.com, 90% of that assessment is based on color alone. And this topic is important because food producers could use this statement to their advantage by coloring their food different colors, and it wouldn't be as healthy as like the ones that are not colored. And people would usually buy the unhealthy ones because it looks better.
So our experiment is we will put 4 types of pastas in 4 different bags, as you can see, and we'll label them 1 through 4. So this being 1, 2, 3, and 4. This one is veggie pasta. This one is tricolored. This one is wheat, and that pasta is plain. So our manipulated variable is the shape of the pasta, because that's going to stay the same and be consistent throughout our presentation. And our responding variable is the participant's choice, because that'll change just because their opinion and how they see the different types of pastas. And our controlled variable is going to be the shape of the pasta, and this shape of pasta is fusilli, and they are all fusilli.
So our hypothesis is that the veggie kind will be the most popular choice. We think this because this has 4 types of different colors, and this is just one plain color. So we think this would be more popular than these 2. And then for this one, this has 3 colors, and this has the same 3 colors. So, but this has the red type, and it would probably, the red type kind of sticks out a little bit more than the 3 colors. So we think it'll be more appealing. So for our graph, it says we tested out 32 people, and 12 people said plain, 6 said wheat, 5 said tricolor, and 9 said veggie. So the plain was the most popular, but if you added the 2 colorful ones together, it would equal 14, so 2 more votes than.
Hi, I'm Chris Pickard, and me and Pasha, we did the dirtiest parts of Bromfield. And so what we did was we swabbed different parts of Bromfield and then grew bacteria inside our homemade incubator, which is right down here. And then we grew the bacteria over a course of 7 days. And we analyzed our data, put it into graphs, gave it a score, and found our conclusion that the cafeteria lunch bin machines had the most bacteria out of all the places in the school.
So what I did was, does heat evaporate various liquids at the same rate? And so my hypothesis was that water would evaporate faster because it contains less material than all the others that I have, as you can see right here. And so I have my data table right here. And so as you can see, my hypothesis was wrong and right a bit. Orange juice, my hypothesis also was orange juice was the slowest to evaporate because it contains the most material. And so alcohol was the fastest to evaporate, not really water, because it has less material. And so to talk about my project, what I did is I labeled all of the liquids that I was going to put. I labeled them on the cup, and then I put the corresponding liquid into the cup, and I put it up to 5 centimeters, which I measured with the ruler. And so I put this at 18 degrees Celsius, and And so I would every day I would write the data down and see how much was left, and I would see, and then I would do this every 5 days, and then so I would every single 5 days I would pour out the remaining amount of liquid, and then restarted the process and pour 5 centimeters of liquid back, and then instead of doing 18 degrees Celsius, I'll do 24 degrees Celsius, which is 75 degrees Fahrenheit. And so, as you can see on the data table right here, the higher the heat temperature is, the faster the liquid would evaporate.
So here's a working jet engine that I built, and this is the combustion chamber. Fuel enters through this pipe, and it combines with air to make a stream of compressed gas going this way. And that hot expanding gas will spin this turbine wheel. And as the turbine wheel spins, the compressor wheel on the other side will spin faster as well, and that will push more air into the engine. And this will become a self-sustaining process. And when more air is being pushed out of the turbine than is coming in, it will produce thrust and push the cart forward. I started this in October, and I put in a little bit of work every weekend, and that's about it.